Good morning, everyone. Thank you for attending this session, how to run simulation workflows in Azure. My name is Tejas Karmarkar. I'm a principal program manager in Azure Compute team, and we work on HPC technologies in Azure. So what we're going to talk about today is what is HPC. Quickly want to run through what kind of HPC workloads we can handle in Azure, which are the target industries that typically use HPC technologies that we try to address. I want to go through a typical tech stack that whether it's on-prem or in the cloud that's typically used, and then talk about some core HPC technologies in Azure that can enable similar type of environment in the cloud, whether it's high performance VMs, whether it's GPU, whether it's our HPC pack scheduler on Windows, RDMA networking, so on and so forth. And then actually I want to do demos. So throughout the session, I will do different demos that show you how to run simulation application. I call it DIY, do it yourself, without any third-party ISV kind of thing, obviously application software. So I will go through different demos, and then we'll slowly ramp it up in the sense first we'll do it yourself with the VM, then I'll show you how you do it with the third-party scheduling software for the burst environment. So if you have HPC on-prem, how do you burst to the cloud? And then I'll demo a SaaS service for HPC for crash simulation built on Azure, and I will show you some applications in Azure Marketplace. So what is Big Compute or HPC? Typically, when you have a job or a task that you want to spin across multiple servers, this layman's term, like you take an application and you want to run it in parallel across 4 machines, 100 machines, 1,000 machines, you can call it HPC. And typically, HPC is used in multiple industries. Financial services do a lot of HPC. All the major banks and insurance companies have regulatory requirements to show their capital assets, what is the risk, what is their insurance risk, stuff like that. They use it for that. Oil and gas, upstream, downstream, across the entire value chain of oil and gas, HPC is used for oil and gas exploration, reservoir simulation, just computational fluid dynamics in general. It's used in climate and hydrology. We have some of the biggest government agencies using Azure to do simulations on. We actually have one government agency running weather or species simulation on 10,000 cores in Azure. And for weather forecasting is another area. Genomics and pharma, there's a lot of molecular modeling going on there, obviously DNA sequencing and stuff like that. Image analysis and processing and rendering, video transcoding. We are working with some of the largest studios in the world to have their render farms come to Azure. Engineering stress analysis, this is my background, automotive crash simulation. Pretty much every automotive company in the world has at least few thousand cores of HPC that they do. Instead of crashing car every time, they want to do a simulation and figure out what their NCAP certifications are and things like that to design better cars. And then we have actually teams internally in Microsoft, and this is another new area, test and build execution. If you're a software development company, if your build processing takes a long time, you could parallelize it across hundreds of machines, and Azure Batch, which is one of our services in Azure, can handle that. So different use cases across different industries. Typically, broadly, we classify the problems, HPC problems, in 2 main scenarios. One is what we call embarrassingly parallel. That's what's typically used in insurance, financial services, is you take a bunch of small jobs. Maybe a job will run for 30 seconds, 40 seconds, maybe a minute at the most, but you run millions of these, right? And you want to keep track of them, and you want to make sure you gather the data from all of them back. We would call that embarrassingly parallel, bunch of small jobs independent of each other. And then tightly coupled, which typically uses message passing interface. That means one job is running across hundreds and thousands of cores, and if one node goes down, the entire job is going to come down. They're not independent. They're dependent on each other through a communication layer called MPI. And that's where the RDMA high-speed networking comes into play, which is super critical to give you the low latency so these jobs can run faster. So typically, HPC, I call it value chain or technology stack. You will see this on-prem, and you can literally lift and shift it into Azure if you want to. Typically, you'll have your own data center infrastructure. You'll have high-speed interconnect if you're running tightly coupled jobs. That's usually use InfiniBand. There are some people who use Ethernet as well. Then you will need a separate network for your Ethernet and storage. Typically, these large environments will have shared storage. So either Lustre as a parallel file system, they might have a huge NAS appliance that's mounted as a single namespace across multiple machines, or you might have GPFS, another parallel file system, or BGFS, something like that. Obviously, you'll have servers. Predominantly, you will see in the industry, HPC industry, predominantly it's x86 servers, right? Then you'll have MPI stack. There are different types of MPIs. Microsoft, we work with Intel MPI right now. There is another MPI called Platform MPI by IBM. And then you will have operating system on the top. You'll have scheduler. Now, typically, if you have hundreds of users using these systems in your company, you want to make sure you schedule jobs so everybody gets a fair share of that system. You don't want one user running 10,000 cores. So you need a scheduler and maximize utilization. And then you'll have HPC applications, which are typically provided by third-party ISVs. These applications in HPC space depend. Some are open source, some are commercial, and they can be very, very expensive. And that's why a lot of our customers want to run this system extremely fast, because they're paying for the ISV license by a year or a paid-up license, and they want to make sure they recover that cost by running jobs as fast as possible, because compute is cheap or got cheap over time. And then you have remote visualization. A lot of companies are looking at doing something like a VDI or a workstation environment with Citrix or some kind of other brokering mechanism. So we can kind of handle the entire stack in Azure, right? So up to operating system, we can do all of that in Azure VMs. We can provide you InfiniBand network. Then you can put HPC scheduler and application on the top, and we can, through our announcement of N-series GPUs, we can provide you remote visualization capability as if you have a workstation in the cloud. So typical applications that we have tested or have worked with and work very well in Azure is a quick list of them. You don't need to, if you're IT pro, you don't need to know these by heart. But if you are talking to your end users or your customers in your organizations, they will recognize these. So NAMD is a molecular dynamic code. It's open source technology. LS-DYNA, PAM crash, and Radios are crash simulation applications. OpenFOAM, Fluent, and Star CCM Plus are computational fluid dynamics applications. Landmark and Intersect are oil and gas exploration apps. And OptiStruct and MSc Nastran are used for noise, vibration, harshness, typically used in aerospace or automotive. Our preferred scheduler, we work very closely with a company called Altair Engineering. They make a scheduler called PBS Pro, and they have an offering called Compute Manager, which I'm going to demo today. That we think that's a preferred scheduler on the Linux systems in Azure for manufacturing customers. And then we have HPC Pack. Microsoft has its own scheduler called HPC Pack, works really, really well on a Windows environment. As I said, we support different MPIs. So on the Linux side, we support Intel MPI. It works on Windows as well. And on Windows side, we have our own MPI called MSMPI. That's for tightly coupled simulations that we just talked about. We support, this is huge, parallel file system in Azure with the support of Intel. It's available in Azure Marketplace. I'm going to show you how to find it. You can provision terabytes and terabytes of volumes in Azure and have a single namespace across multiple machines. Now, you can use it for HPC, but you might use it for something else too, right? Depending on what kind of applications you're running, this is huge because you can provide, like I can do 5 Lustre OSS servers attached 5 terabytes, and I have 25 terabytes single volume, stripe across 5 file servers, and present that as a single namespace across hundreds of machines. So it's like a shared storage with good performance and with the reliability of a parallel file system now available in Azure through Lustre. There's another parallel file system we work with called BGFS. It's being worked on. On the operating system support, so this is again a big change coming from Microsoft. Obviously, we've been working with Windows for a long time. We are Microsoft, so Windows Server 2012 R2, Windows Server 2012, and 2008 R2 are supported for RDMA networking or HPC apps in Azure. And we launched Linux RDMA last year in July. Since then, our utilization has just gone through the roof because a lot of HPC industry uses Linux. So SUSE 12, /12 SP1, CentOS 6.5 and 7.1, and we are working on a Red Hat. So this is to enable InfiniBand backend network called Linux RDMA. Now you can provision 1600 core clusters in Azure and run your parallel jobs across thousands of cores. And we do that on Linux, and we do it really, really well. So some of the technical prerequisites to run an HPC job in Azure, right? I'm coming more from tightly coupled environments, so some of this applies to embarrassingly parallel workloads as well. But first of all, you need high performance VMs. As I said, high performance VMs that will give you extreme low latency. When I say low latency, we're talking about 2.6 to 3 microseconds. And bandwidth up to 32 Gbps or 56 Gbps between the nodes. You need shared storage. That's why either you can use NFS or you can use parallel file system. You need passwordless SSH between the nodes. So a lot of tightly coupled jobs are not going to run if you don't have passwordless SSH between the nodes. Now, don't do it. If you're going to do it, don't do it for root because it can be a lot of security risk. So make sure you do passwordless SSH for the non-root users on these machines so they can run the jobs. Typically, we would recommend that you have a virtual network because a lot of these systems want to connect to on-prem environment. And if you have a virtual network in Azure, you can control the IP range and you can close certain ports off, like public ports and things. You get a very granular control that you would want. And then typically you need a scheduler if you have more than one user. So let's talk one by one. Azure high performance VMs. So these are the VMs our team works on. There obviously you can use other types of VMs in Azure. There is nothing stopping you, but if you want to run tightly coupled applications that use MPI, you want to use either A, H, or N depending on which technology you want. So we recently, A8, A9 are InfiniBand enabled nodes, and A10, A11 are in the same series. They don't have InfiniBand network. So you have A8 to A11, which has already been there for, I believe, 2.5 years now. It's a little bit older processor with Sandy Bridge. It has QDR InfiniBand with 32 Gbps network, 3.2 microsecond latency. Pretty good system. It's getting a little older. So we announced our H series. You probably heard Jason Zander talk about it, and maybe I have a blog. So H series these are some of the fastest VMs in the cloud on a virtual core performance, right? vCPU. So it has 3.2 gigahertz base frequency. With turbo, it can go up to 3.5. We have memory up to 224 gig of memory with DDR4. We have up to 2 terabyte of local SSD scratch on each machine, and it has FDR InfiniBand with up to 2.6 microsecond latency. So as you see, we have tried to boost performance from A8, A9, or A series to H for HPC. More bandwidth, lower latency, more local SSD storage, more memory, and the fastest processor in the cloud. And then we have N series, which are our GPU machines, GPU VMs. They are either M60 or K80. K80 typically used for compute, and M60 used for visualization, I'm going to show you today. And then it has a high front-end bandwidth network through Ethernet, and it also has up to 2 terabyte of local SSD. So think of this GPU M60 machine as an engineering workstation in the cloud. You could potentially use it like that. I'm going to show you how you can do it today. So why InfiniBand RDMA matters, right, for tightly coupled applications. This is a crash simulation code called Radius from Altair Engineering. And you see the performance close to bare metal. So bare metal means these guys had the servers in their data center, no virtualization. They were running it with a similar kind of setup with Sandy Bridge. This was done on A9s in Azure on Sandy Bridge processors and QDR InfiniBand. You see the performance almost identical as you start scaling the job up to 200 cores. In some instances, even faster. So, you know, InfiniBand matters because as you start scaling the job, if you don't have a low latency network, the messages that are passing between the nodes are going to get delayed or they're going to get blocked. And you see, here I'm running a job across hundreds of cores. This was actually run on a competitive cloud. I've taken the name out because I don't want to mention it here. It was done with another large public cloud vendor, and they don't offer InfiniBand, and we do offer InfiniBand. So as the number of cores increase, you want the job to run faster, so the slope should be, you know, amount of time required to run the job should be going down over time. And as you see, after 64 cores, after 64 cores, actually the job time starts increasing if you don't have InfiniBand. And typically you will see 128, 256. Some CFD applications we have ran tests, I have blogs online up to 1024 cores, which is almost impossible to do if you don't have InfiniBand. And that's why we made a conscious decision to invest what I call no compromise HPC. We want to give you exactly similar type of capability that you have on bare metal on-prem in the cloud and give you same type of performance. We're not saying these are a bunch of web servers you can use it for and do your HPC on the side there. We're giving you dedicated infrastructure for HPC in Azure. So that's why InfiniBand matters. Go ahead, you have a question. Yes, so RDMA over Ethernet, that's called RoCE. RDMA over Converged Ethernet. And so RDMA over Ethernet is possible, or you can do it over TCP, but TCP latency is very high. But there's RDMA over Converged Ethernet, which is similar to InfiniBand, but the latencies are still higher. We do evaluate it from time to time. And then RDMA over InfiniBand is what we have. So RDMA is remote direct memory access. It gives you an ability to connect with the network. So RDMA is available across different stacks. Here it's on InfiniBand. You won't see same kind of performance. You will see it still slower. And that's why majority of the industry is still using InfiniBand. But RDMA over Converged Ethernet is not bad. It's not as bad as just Ethernet, like low-grade Ethernet or whatever you want to call it. Yeah. I know what the other cloud vendor uses, and I believe they use SRIOV, which is single root IO virtualization. But they have a 10 gigabit Ethernet network, and here we have 32 Gbps network, and the latency is 3.2 microseconds. So I don't know what the latency is, but it's definitely not 3.2. Latency is really, bandwidth doesn't matter a whole lot. If you have a decent pipe, it should be okay. Did I answer your question? Okay. So there is a shared storage available. Obviously, you can do NFS. There are templates available on GitHub that will set up your entire cluster with NFS shared storage also. You can go look it up under Azure branch, done by a lot of people who work at Microsoft and others as well. And then there is a Lustre available in Azure Marketplace. So there is a quick snapshot. I took a picture of how it looks like. You can build this system, Lustre shared storage. You can build it with any VM. But if you really want a fast parallel file system, you can do it with the DS series. nodes, DSV2. These are the latest generation. You can go up to DS14, which is the highest machine. The reason you want to do that is the biggest machine in DS series because you get maximum bandwidth for the front-end Ethernet network, which is going to push the data onto your storage or Lustre storage. And then you want P30 disk. That's a premium storage disk that gives you the best performance backed by solid-state drives. And then you can deploy, I do this regularly, I can deploy 1600 core cluster. We are trying to lift that limit up to 5,000 in near future, but you can deploy 1600 core cluster with 20 terabyte of shared storage literally in 10 minutes. It's available through template, and I will quickly show you how to do that. So this is really powerful, and you can use this not just for HPC, you might be able to use it for other stuff as well if you need a shared storage. Passwordless SSH, there is one of my colleagues, Taylor Newell, he wrote a script to do this. Instead of doing it manually, he wrote a script. So there are lots of, if you can go online, this is the beauty of doing this on Linux, right? You can go online and there'll be lots of discussion about it. You'll find commands to do it. But there's a script available on GitHub written by Taylor for CentOS. It basically doesn't matter how big your cluster is. You have 10,000 cores with, I don't know, 10,000 would be 500 machines. It will go do SSH trust auth between 500 machines quickly for a user. And then VNet setup matters. So here you have a schematic where I have kind of typical HPC environment. When you want to connect to on-prem, the virtual network, the boundary of a virtual network is kind of controlling the access to all the VMs, whether it's for storage, whether it's for compute, whether it's a head node that you can do NATing, stuff like that, to provide HPC capability in the cloud. That's why virtual network really matters, so you can control the environment nicely. So I'm going to quickly move to a demo machine and show you how you can run a job on a Linux VMs and then do post-processing for crash simulation here. So the way I'm doing this demo is, this is a M60 GPU machine in the cloud in Azure, and I'm RDPing into this machine basically. And I'm thinking of this machine like my desktop. So if you have end users that are doing engineering simulations, you can literally provision a machine for them where they can do everything, right? So if you have access to GPU, this can be their engineering desktop. Here I have a Windows Server OS, and I use this utility called MobaXterm. It's free download. You can go online and find it. But I can use PuTTY or anything to interact with Linux machines. And I have logged into a cluster here, and I'm using a simple script. I'm old school, so I'm still using VI. So I have a simple script here. You don't have to worry about what is in the script, but we will make this available online. But I'm running a 256 core job for a software called Lustre, which is a crash simulation code across 16 servers with InfiniBand RDMA on A9s. So all I do is, this is what I call do it yourself. So if you have one user, 4 users, you can give them 16 node clusters to each of them and say, this is your playground, go run your simulations here. It doesn't have to be complicated. It could be as simple as this. I'm doing this for LS-DYNA, but you can do this for a CFD application, OpenFOAM, whatever application you're running. This could be as simple as that. And I will show you in a second a deployment script that I use to deploy the cluster. So it's running the job. It will run for maybe a couple of minutes, and it's running across, it says 17 minutes, but it will run faster than that. And I want to show you the script that I use to launch the cluster. In this case, I'm showing you oops, I've logged into a different machine. But basically, I'm using ASM, which is RDFE, ASM technology to launch the cluster, and I'm simply running jobs on it. as you see, the job is going through different time steps. So while it's crunching the job, let me show you. So once the simulation is finished, I want to do post-processing of the job. So I've launched an application here called HyperView. It's an independent ISV called Altair. They make simulation products, so I've launched this product called HyperView, which uses OpenGL graphics technology. And I'm going to load the result files that I'm computing, that I already computed for a crash simulation. So this is open source model available online called 3car. So it's basically crashing 3 cars and doing simulation of it. Important thing to note here is that I'm doing this on a GPU machine in Azure, right? So this is running in our San Antonio data center, south central region of Azure. And you will see the performance. It's pretty good. And I'm doing this over RDP. If you use something like one of our partner solutions like Teradici or something, it will be even faster. I'm using like free RDP that comes with Windows Server. And I'm going over a Wi-Fi that all of you are connected to as well. No, I'm sorry, I'm using connected network. I was on a Wi-Fi before, sorry. But it's not like the highest speed network, right? If you're at your office, you probably get better bandwidth. So the point is, if I'm an end user, I can log on to my GPU machine and pretty much do everything from there. This tool is great. I can literally point to a bunch of files, and I simply say download. All I have to do is point to a directory. It will start downloading files. So if you have a Lustre server, you can get one of these utilities, or you can do Samba mounts onto the Lustre. So you have a GPU machine in the same virtual network as your cluster, and then you have shared storage there. So if you do a Samba mount, you can point to the right IP address on the same network and map the drive, and then you're basically transferring the data. And this graphics capability will be available on Linux as well. So you might have a CentOS system doing the same crash simulation post-processing. In that case, you don't even have to mount anything. You just have a same mount point for Lustre onto the Linux OS, and it appears as a storage for Linux. So extremely powerful. You can, you probably set up these machines for your user on-prem with this big desktops. Now you can do it in the cloud and control all your simulation workflow right from one location. So with that, while the job is crunching, let's move back. So the burst scenario, where basically you already have existing infrastructure on-prem, right? You have invested, you bought servers. You're not going to move everything to cloud right away. You can connect through, if you're familiar with ExpressRoute and VPN, you can, in Azure, you can connect through that to a cluster in Azure. That's where, again, the VNets are very important, because then you can have a gateway and you can control the IP range so it doesn't conflict with your servers on-prem. And then you can use VM scale sets as well and virtual machines to create clusters in Azure. So I do want to switch back to demo now for a typical burst environment. This is what we see in enterprise space. Largest oil and gas companies, automotive companies use Altair's solution called PBS Pro, one of our partners. And we have implemented this across thousands of cores today on Linux systems in oil and gas and automotive, where they're using it to burst to Azure. So I'm going to move back to 8. So you see the job finished in 244 seconds, 4 minutes, 4 seconds, and I could just download the files and look at the results. So let's talk about this solution from Altair called Compute Manager. So this is completely hosted in Azure. So again, if I'm an end user, I can log on to my GPU box. It's in the same VNet. And I will basically have an IP address or web address that I could log into. In this case, Altair has hosted this on Azure servers. So I'm not in a VNet right now. So I'm just logging onto a website which is hosted in Azure. The entire infrastructure is hosted in Azure. But this could be controlled through VNets, and it will be only accessible if you're on VPN and you're connecting through VPN to on-prem, or if you're on your office network, or you can log into a GPU box as I'm doing and have an engineering workstation in the cloud and log in. So it's basically a scheduling environment with a very, very good front-end interface, right? So as an end user, I would come here, and if I want to submit a job, again, a crash simulation model, I can simply go and I'm going to resubmit this job, so I can walk you through the interface. So here they have listed different solvers that Altair offers, right? So Altair is a simulation company as well, and they do scheduling software and compute manager. As you see, different solvers are available. I'm running a job for a solver or application called Radios, which is a crash simulation code. And as I can see, I can select different versions. I can give it a job name. I can define how much memory I want. I can upload, just browse and upload the files. And I simply say submit or resubmit in this case. As soon as I do that, my job will go into the monitoring queue, and you see it's off and running. So this type of system is very, very, very common. PBS Pro is very common in HPC environments. There are lots of companies, and they use it today. The beauty of this is when I'm running a job, like this is a job that finished, all my files are available here. So I can simply click on a file, and I can download it. My file is there, and I can quickly go and look at the results again. So maybe we should go and load the model. So that's the simulation that I ran using Compute Manager. And this is, again, this is a Dodge Neon car. It's open source model available online. So I just showed you that how you can burst using an existing scheduler. If you have Compute Manager, if you have PBS Pro, you can easily set that up in such a way that you can burst to Azure to run more jobs. And those files after running the job are easily available for you to download. And then you can do post-processing again, all on a GPU workstation in the cloud using M60 NVIDIA cards. So you'll see that the job is still running. While it's running, I have access to all the files. So if I want to go and monitor how my job is, a lot of times end users would want to go back and they want to monitor how the files are running. So I have access to all the text files here that I can go and scan, and I can look if there are any errors, any problems, stuff like that. Let's switch back. So that's the burst scenario where you already have existing infrastructure and you want to leverage cloud for more capacity. Now let's talk about SaaS. So we work with a lot of ISVs, a lot of companies that want to build SaaS solutions in Azure. That means your end-to-end solution. So I'm going to demo a solution here called D3 View. Think of it as doing crash simulation as a service. So as an IT pro, you can set up that environment or a SaaS service for your end users. Just make sure it's securely connecting to your network, and off you go. You don't have to maintain anything. You don't have to load applications, things like that. And a lot of ISVs, if you're ISV here in the audience, and if you want to build a service, this is how some of our customers are doing it. And we have a very interesting technology called Azure Batch. Azure Batch is a service today, and it's kind of built on basically VMs and some of the cloud services in Azure. And these are the things that we just talked about, right? Do passwordless SSH, move the data, create a parallel file system. And that is all required because you want to communicate between the servers, you want to move the data around. We're doing all that in infrastructure as a service, like we are provisioning a bunch of VMs and we're connecting things together. If you don't want to do all that and you want to build a service, Azure Batch is the solution, right? And it has a built-in scheduling technology as well. So what it will do is it will keep track of your task. If the task is failed, it will requeue it. It has all the functionality that you would want in a scheduler, and you can interact with this service through APIs, and kind of Azure Batch will take care of all those things that we just talked about. And you can interact with, as I said, with the service through APIs, and you can build end-to-end simulation service on top of Azure Batch. We do have some actuarial modeling companies like Tower Watson and Milliman are leveraging this type of technology to offer actuarial modeling for insurance companies in Azure. So Azure Batch is extremely powerful. We have done scale testing up to 100,000 cores to run insurance simulations, and you can use that to build a SaaS service. You can build a SaaS service on top of a bunch of VMs as well, but Azure Batch is obviously a very, very interesting option. So I'm going to demo D3View SaaS service. This is built on VMs. It's not built on Azure Batch, to be clear. But it's a crash simulation service built by a company called Xfinity, and their brand is D3View. So we'll quickly switch over. So my job is still running through Compute Manager. We'll close that. And so this is a D3View hosted in Azure. Again, I have a web address that I'm signing into. So I'm signing into D3View portal. D3View is a very interesting technology. As you see, the scheduler interface looks very similar to Compute Manager. I can submit a job and I'll see it in the queue. But they do a lot of stuff on automatically extracting data from your simulation and help you visualize the data, and I'll talk about that in a second. So I'm going to submit a new job here. This is simulation service for a crash or crash simulations. Very nice interface. I can quickly upload my input file. And here I'm selecting a bunch of servers already provisioned up to 160 cores. I'm not going to run 160 core job here, but my cluster is pretty large. I say add a configuration, and I have to give a description. And there we go. I say submit. And now I uploaded that file from my desktop, in this case my engineering workstation in Azure, and it's taking all my input files, submitting job to the SaaS service called D3View. So if I come back, here it shows the status submitted, and now it's in a solving stage. So it will keep giving you status. It actually sends you emails as well. I have my Outlook client disabled because I don't want to get email, but it will send me emails and say your job is queued, your job is running, your job is solved, you're ready for post-processing and things like that. So let's look at one of the jobs that I already ran, where the entire post-processing is already done. This is what I mean by what D3View is really good at, is they'll not only run the simulation, show you status, but they'll extract all the data for you. So in this case, we are extracting airbag pressure, airbag volume. It already extracted the videos of the simulation that already ran. So this is typically, you will see airbag manufacturers, automotive OEMs do these types of simulations. So what D3View is doing, it knows what to extract, right? Because it's built a service for crash simulation. It's automatically extracting the data, pre-populating it in a format that you would want to use using templates, and it's all completely customizable. So I'm not only running simulations now, I'm running simulation and I'm extracting the data. So it's a very, very interesting technology, and it's all built on Azure. So if I want to go and compare some of the simulations, I can simply, if I want to create a quick report, I can select a bunch of simulations and I can say compare. And I have a pre-populated template that I'm going to use, and I simply say OK. So it will do number crunching, and it will extract all the data that I want, like a peak pressure, mass flow, different volumes of the airbags, and it will show me the comparisons. See, so it's plotting curves of 3 different simulations on top of each other. This is what typically your automotive engineers, your simulation engineers want to do. They run simulation, they want to compare what I did before, what was the airbag pressure in the previous run. So that's easily possible. They also have a tool called Simulytics. What Simulytics does is it gives you an ability to visualize your data in different ways. So here I have ran a design of experiments, which is basically, if you're familiar with statistics, you can quickly go online and find what design of experiments is. It's basically running permutation combinations. So in this case, actually I'm doing structural crash simulation where I'm changing the thickness of the bumper, the thickness of the hood of the car, and I'm trying to figure out what is impact on a pedestrian's head when it hits the hood in a pedestrian crash. So I've said, okay, I want to have my hood at thickness of 1 millimeter, 4 millimeter, 5 millimeters, 10, whatever that is. And then I said my bumper thickness has to be 2, 4, 6, 8, and I'm trying different materials. So I'm trying different combinations, and I want to make sense of it, right? As if my thickness for bumper is 4, what is the impact on the head acceleration when the pedestrian hits his head on the hood? So here I'm just visualizing data different ways where my thicknesses are changing and my head acceleration. So I'm trying to figure out using the data visualization capability available in D3 View for my design of experiments. While it's doing that, we can look at another chart. Here I have, again, different results coming from my DOE analysis. You say T bumper means I'm looking at the thickness of a bumper, so I can simply come here, and if I drag, I'm selecting different thicknesses of a bumper, and as I select them, it's showing me what is the thickness of my hood, what is the head acceleration means hic, and what is the mass, and what is acceleration, maximum acceleration for the head of a pedestrian. So I'm easily able to visualize the data for my simulations using a tool in D3 View. Here is another chart where it's showing me different head acceleration for different thicknesses of a bumper. So here we are not just running one simulation at a time, we ran a bunch of simulations and we extracted the data using a service in D3 View to make sense out of hundreds of simulations at once. I'm sure there are other commercial tools available that will do this, but this is all hosted in Azure, this is all running in Azure, so you're not only doing HPC, but you're doing data extraction and data mining using a SaaS service called D3 View. So let's move back. How are we doing on time? Okay. There are HPC applications available in the Azure Marketplace as well. So what Marketplace does is it really gives you ability to reach millions of users around the world, right? Azure Marketplace is available in hundreds of countries. It's very simple to deploy, and I'm going to walk you through that right now. Very simple deployment, everything is pre-packaged already. So if I want to run computational fluid dynamics code, I can simply go to Azure Marketplace and look for the right application, and I go deploy a VM, I remote log into the VM or SSH, and I'm in business. So very, very easy way to use Azure Marketplace applications to do HPC. And we are working with multiple ISVs, but one of the interesting ISVs is called UberCloud. It's a company out of Bay Area, and they have 4 applications available in Azure Marketplace today. The first one is called OpenFOAM. That's a computational fluid dynamics code. I'm going to show you, I'm not an expert in OpenFOAM, but I'm going to show you how, once it's deployed, how it looks like. Then we have Star CCM Plus, which is a computational fluid dynamic code from a company called CD Adapco, which is a part of Siemens now. And then we have Star CCM Plus with HEEDS to do multidisciplinary optimization very interesting technology. And then we have ComSol's multi-physics available as well through UberCloud offering. What UberCloud has done very interesting, they have Docker technology embedded within their VMs, and they have actually enabled RDMA networking, high-speed networking through Docker as well. So you not only have a VM, on top of that you have a Docker container, and through Docker container you can do low latency networking between VMs. So it's very, very interesting what they're doing. And OpenFOAM is open source code, so you don't really need a license. If you want to do computational fluid dynamics, you can literally go in Azure Marketplace, launch application through UberCloud called OpenFOAM, and you can start running simulation. The other 3 applications require a license. So what that means is everything will be deployed, the entire environment will be ready. You just have to call your ISV and say, give me a license. Here is a MAC address of my VM, and you will have to procure a license, or you can use your existing license on-prem in the cloud or something like that. But the first application doesn't require a license. So let's quickly switch again, and I want to show you how it looks like. So it's a simple, as soon as you launch a virtual machine using UberCloud, you will get an email, and it will have a password, and you could log in using a link basically. But before I do that, I want to show you how you actually launch that. So everybody is familiar here with the Azure portal. You go to Azure portal under VMs, and I just search for UberCloud. As I said, they have 4 different offerings available in Azure Marketplace. And I'm going to select the first one called OpenFOAM, and it uses Resource Manager. It says what is pre-installed software available in their container. I say create. I have to go through a standard template. It's using Linux VM, so it's asking me for a password or SSH key. I give it a subscription. Resource group, I'm going to create a new one. And in South Central, so I say OK. And it goes through the entire workflow. I have to select which size I want and things like that, and so on and so forth. So if I walk through the entire process, let's just select this for now. See, it's pre-populating everything, so it's a containerized environment with everything ready to go and secure. So it's already pre-populating storage account, it's pre-populating your network. There are no extensions here. If you want availability set, and you simply have to say create OK. It's running through validation. Actually, I'm using a free internal subscription in Microsoft, so I don't have right to actually buy this in Marketplace, but once the validation is done, you should be able to go to next step and actually purchase it. There we go. So it's actually showing you the cost. So it's very transparent. It shows you what the cost is, and you can simply the cost of a VM and cost of their software. And then you can say purchase, and then once you purchase that, you will get basically email with the link. You click on the link with the password. For some reason, because I'm RDPing and the connection with the projector here, it's not displaying the interface correctly, but that shouldn't be an issue when you're doing it. So this is a ParaView, which is open source pre and post processor for OpenFOAM. And I'm not an expert in this software, but you should be able to interact. And again, I'm running this. You could go and select an N-series machine, so a GPU-based machine to do this compute in a Docker container, and you'll be able to utilize a GPU machine. In this case, just a simple VM that I'm logging into through a web interface or through VNC. But the important part here is it's all pre-packaged. You simply have to go do a few clicks, and the entire environment is deployed for you. That's the beauty of it, right? So let's switch back. So who is using, we have some customers that are already, a lot of customers, we can't talk about them publicly, but we have a case study from CFD support where they use UberCloud container technology in Azure to do their HPC, solve their HPC problems for computational fluid dynamics. I'm very happy with that. We do have other customers that use the technology in Azure on thousands of cores. One good example is Hendrick Motorsports. They use it for computational fluid dynamics problems. Can't disclose exactly what they were doing, but they were using for to optimize their exterior structures of their cars for NASCAR races. And they didn't want to buy thousands of cores, and their utilization varies throughout the year. So why make a multi-million-dollar investment if we don't know if we're going to use it every day? We need it when we want to solve problems. So they decided to use Azure to run their CFD problems, and they're running it on thousands of cores. So I'm a very happy customer. I'm going to quickly show you a video to make HPC very exciting. They're obviously using multiple technologies and not just HPC technology. So in a video, you will see how they're leveraging visualization technologies, Power BI, OneNote, lots of other technologies in Microsoft Cloud along with HPC. So we'll quickly play the video.
The goal of Hendrick Motorsports is simple: to win races and to win championships.
What makes us go is fuel, tires, and technology. Having the ability to maximize our fuel distance, to maximize our tire life, and using the technology and the information available to get both of those things is what produces a winning setup.
Everything that we do around the race car and our race engines has technology threaded through it. It's where we look for an advantage.
Green flag is in the air. We're under.
Trying to gain an advantage in your car is very, very difficult. Being able to process more information faster, you can make more decisions about your car. That's where technology becomes huge. I don't want every bit of information, I want the results.
I used to think Microsoft is a software company, and what I'm really finding is they're a solutions company. Windows 10 integrates nicely with the cloud, and it's really our gateway to leverage Cortana Analytics and the machine learning suite to process the data in an automated fashion. Windows 10 does a really good job of allowing mobile continuum and for those guys to be able to switch back and forth from multiple computers, multiple machines to get the information they need in a timely fashion.
Since winning is defined by 1/10 of a second, data analytics can help determine our pit windows, and it can really improve a lot of our time on the track.
What's really beautiful about the Microsoft Cloud is it allows us to leverage computing power, and as the race starts, we may spin up 1,000 cores, more computing power for the event, and when the event concludes, we turn that off. So with Microsoft's Cloud, we really just pay by the minute, and we don't incur the $200,000 cost to buy hardware.
The nice thing about Office 365 is that we can start to collaborate on a higher level.
It's so loud at the racetrack. We're using Skype for Business to chat to our teammates during practice. I'm talking to all the other race engineers on top of the pit box.
What OneNote does and what SharePoint does is it allows us to do development at a rapid pace. We're able to have the same communication as if everybody was pulling in the same direction, and that's really powerful.
What's exciting about this relationship with Hendrick Motorsports and Microsoft is that with Windows 10, Office 365, and the Microsoft Cloud, it's enabling our engineers to do more and achieve more.
Isn't that awesome? When you see HPC technology being used by a race car company like Hendrix, it's really phenomenal to see. So in conclusion, we went over like 4 main scenarios that I just showed you how you can run simulations on a Linux machines. I call it DIY, do it yourself. You can easily spin up machines in Azure and run your simulation workloads using InfiniBand RDMA. something like crash simulation. So we saw that. We saw burst capability through our partners like Compute Manager PBS Pro from Altair, how you can use a scheduling environment that you're already used to. Then we saw a SaaS service from a company called D3View that provides you a SaaS service in Azure for crash simulations. There are lots of other SaaS services available that are built on top of Azure as well. And then we saw Azure Marketplace, the beauty of using Docker containers through technology offered by UberCloud to have a prepackaged solution in Azure Marketplace that you can quickly deploy and have your users use it. So all in all, we can provide you simulation technologies in Azure through our HPC core technologies, whether it's GPU, whether it's high-speed networking, whether it's fastest VMs in the cloud, all that can be available at your doorstep to do HPC workloads in Azure. So with that, I want to quickly point your attention to, we have developed a microsite called simulation.azure.com, and you can always go there. We try to update our latest blogs, and instead of having you go to multiple sites to figure out information, we try to concise it in one site where you can go and get more information. You can ask us questions there. The GPU preview is on that site too, so if you want to get access to a GPU preview, you can go there and put a request. So there's some free IT Pro resources. I've been asked to put this slide. You can go how you get started with Azure. You can connect with your peers, and you can see demos and videos. So with that, I can kind of open it up to questions. We are ahead of schedule. We have about 15 minutes, so I'll be more than happy to take questions. So we haven't looked at that yet, but that's something we'll look at it in the future. We haven't tested that yet in the HPC team, at least. Yes. Yes. Yes, I'm not using temp. Yes, so it's going to use templates behind the scene, the ARM templates, underneath the covers. Yes, but it's all pre-packaged, pre-integrated, so you don't have to worry about developing a template yourself. Yep. And it's available through HPC Pack as well. So HPC Pack has a bursting capability available also that can be for Windows or Linux. So I showed a example. So what I showed here is not the only way. I've picked certain examples that I thought were relevant, but there are other ISVs, there are other SaaS services that are built on top of Azure. There are other ways, as you pointed out, through HPC Pack. So there are different avenues. I just showed kind of a sample that I thought would be useful. Any other questions? Thank you so much for attending. Don't forget to fill your feedback, and so we can do this session again hopefully next year. Thank you.